Definition of smart contracts. Smart contracts are self-executing contracts with the terms of the agreement directly written into lines of code. They automatically enforce, execute, and manage the terms of a contract upon meeting predefined conditions, without the need for an intermediary. Imagine entering a vending machine scenario into a digital form. Instead of inserting coins and selecting an item, a smart contract would automatically transfer funds from your account to the seller's account once predefined conditions, e.g., confirmation of item delivery, are met. This ensures a trustless, efficient, and direct transaction between the parties involved, without the need for a middleman or manual intervention. History and development of smart contracts. The concept of smart contracts was first proposed by Nick Szabo in 1994, long before Bitcoin or Ethereum. He envisioned smart contracts not as a specific piece of technology, but as a set of protocols that could execute terms of a contract automatically. With the advent of blockchain technology, smart contracts became a reality. They are self-executing contracts with the terms of the agreement directly written into lines of code. This sample Solidity code represents the basic structure of a smart contract in Ethereum. It doesn't execute any sophisticated logic. It's merely a placeholder to illustrate the simplicity of initiating a smart contract. Crucially, the real power of smart contracts lies not in their structure, but in their ability to execute complex agreements without the need for intermediaries. These contracts run on blockchain technology, ensuring transparency, security, and trust by design. Since their conceptualization, smart contracts have evolved, becoming central to various blockchain platforms and applications beyond Ethereum, driving innovation in many sectors. Blockchain basics and smart contract platforms, Ethereum, Binance Smart Chain, etc. To understand smart contracts, we first need to dive into the underlying technology. Blockchain. A blockchain is a distributed ledger that is open to anyone and is used to record transactions across many computers. The technology ensures the integrity and security of a data record thanks to its inherent characteristics like immutability and decentralization. Smart contracts are self-executing contracts with the terms of the agreement directly written into lines of code. This Solidity code snippet defines a simple smart contract on the Ethereum blockchain platform. The contract, simple storage, allows users to store and retrieve an unsigned integer. The set function allows a user to store an integer, while the get function returns the stored value. Solidity is the programming language used for writing smart contracts on Ethereum, showcasing a fundamental example of how smart contracts operate in conjunction with blockchain technology. Smart contract languages, Solidity, Viper, etc. Smart contracts are self-executing contracts where the terms of the agreement between buyer and seller are directly written into lines of code. These contracts run on blockchain networks. The choice of programming language is crucial for creating secure and efficient smart contracts. Two of the most popular languages are Solidity and Viper. In the Solidity example, a contract named greeting is defined, setting a public string variable greet with the value hello world. Solidity is statically typed and object-oriented, making it a popular choice for Ethereum smart contracts. The Viper example shows a similar hello world contract. Viper aims for simplicity and security, avoiding some of the complex features of Solidity. It uses Python-like syntax and focuses on readability and auditability. Both languages compile to Ethereum Virtual Machine, EVM, bytecode, but approach smart contract design with different philosophies. Development environments and tools, Remix, Truffle, Hardhat. Developing smart contracts requires a supportive and feature-rich environment. Remix, Truffle, and Hardhat are among the most popular tools for Ethereum smart contract development. Each has its unique features tailored to different stages of the development lifecycle. This Solidity snippet defines a basic smart contract using the pragma keyword to specify the compiler version. The Hello World contract contains a function, say hello, that, when called, returns a simple greeting. In development environments like Remix, this can be quickly tested in browser. Tools like Truffle and Hardhat offer command-line interaction, testing frameworks, and additional deployment functionalities for more complex development and testing processes. Writing your first smart contract. Smart contracts are self-executing contracts with the terms of the agreement between buyer and seller directly written into lines of code. The code and the agreements contained therein exist across a distributed, decentralized blockchain network. Smart contracts permit trusted transactions and agreements to be carried out among disparate, anonymous parties without the need for a central authority, legal system, or external enforcement mechanism. They render transactions traceable, transparent, and irreversible. This is a basic example of a smart contract written in Solidity, the programming language designed for developing contracts on the Ethereum platform. The Pragma line specifies the Solidity compiler version to ensure compatibility. The contract is named Hello World, encapsulating its functionality. Inside it, a string variable greet is declared with a public visibility modifier, meaning that the value of greet can be accessed by anyone interacting with the contract on the blockchain. The value of greet is set to Hello World, making this contract simple yet illustrative of how a piece of data is stored on the blockchain via a smart contract. Understanding smart contract structure and syntax. Smart contracts are self-executing contracts with the terms of the agreement between buyer and seller being directly written into lines of code. The structure and syntax of a smart contract are crucial for ensuring its efficient and secure operation. Let's explore a simple example using Solidity, a programming language for writing smart contracts on Ethereum. This code defines a smart contract in Solidity named Simple Storage, which stores a single unsigned integer. First, we specify the version of the Solidity compiler with Pragma Solidity 0.8.0. The contract starts with the keyword contract, followed by the name Simple Storage. Inside the contract, we declare a state variable stored data of type uint, unsigned integer. Two functions are defined. Set allows the user to store a value in stored data, and get allows anyone to retrieve the value of stored data. The public modifier makes these functions callable from outside the contract, and view in the get function indicates that it doesn't modify the state of the contract. Variables, functions, and modifiers. In smart contracts, variables store data, functions define the logic, and modifiers set conditions for functions. Variables can hold state information, functions perform actions, and modifiers ensure that certain conditions are met before executing a function. We'll illustrate these concepts using a simple contract in Solidity. This code defines a contract simple store with a public unsigned integer variable store value. It has a function set that assigns a value to store value. The only positive modifier checks if the input value is positive before the set function can update store value. The function set uses this modifier, indicating that store value can only be set to a positive number. This example encapsulates the use of variables to store data, functions to perform logic, and modifiers to enforce rules. Events and logging. In smart contract development, events are hooks that allow you to react to specific contract actions externally. They log activity in the blockchain for efficient off-chain consumption. This is especially useful for creating a history of transactions or signaling to external consumers, like user interfaces. In this smart contract example, there's an event named valueChanged, which gets emitted every time the setValue function is called. The event logs who called the function, author, the old value of the contract's value field, and the new value being set. This emission allows external observers, like DApp interfaces, to react or display the updated information without constantly polling the contract. Emitting an event is also gas efficient compared to storing or manipulating additional state variables for logging purposes. Inheritance and interfaces. Inheritance allows a contract to acquire properties and functions of another contract, promoting code reusability and organization. Interfaces define a contract's external functions without implementation, enabling interaction between contracts. The interface iCalculator defines a function add without implementing it, specifying a blueprint for other contracts. The calculator contract then inherits and implements the functionality of iCalculator. Using override in calculator's add function indicates it's implementing the interface's function. This pattern ensures calculator provides the specific functionality defined by iCalculator, exemplifying a contract-to-contract interaction framework typical in decentralized applications. Deploying contracts to a test network. Deploying smart contracts to a test network is a crucial step before launching them on the mainnet. This allows developers to test their contracts in an environment that simulates the main network without risking real assets. We'll use Truffle, a popular development framework for Ethereum, to deploy a contract. The command truffle migrate network Ropsten is used to deploy contracts to the Ropsten test network using Truffle. Truffle migrate initiates the deployment process, compiling your contracts and deploying them to the network. The --network Ropsten flag specifies which network in your Truffle configuration to use for the deployment. Before running this command, ensure you have defined the Ropsten network settings in your Truffle configuration file, including the network URL and account credentials. Reentrancy attacks. Reentrancy attacks are a common vulnerability in smart contracts, particularly those which interact with external contracts. They occur when an attacker exploits the fact that a contract calls an external contract before updating its own state. This can allow the attacker to repeatedly call the vulnerable function, draining funds or corrupting the contract's intended logic. In the provided code, vulnerable bank is a simplistic contract that allows deposits and withdrawals. The vulnerability lies in the withdraw function. It sends ether with ms.sender.call value or score amount before updating the sender's balance. Balance is mes.sender score amount. An attacker contract calling withdraw can re-enter the withdraw function before the balance is updated, allowing the withdrawal of more ether than the attacker's balance should allow. This can lead to funds being drained from the contract. Arithmetic overflows and underflows. In smart contracts, especially those written in Solidity, arithmetic operations are constrained by the data type's maximum and minimum limits. Arithmetic overflows occur when an operation results in a number larger than the maximum possible value, causing the value to wrap around and start from the minimum value. Similarly, underflows happen when an operation results in a value smaller than the minimum possible value, causing it to wrap around to the maximum value. These vulnerabilities can lead to unexpected behavior and can be exploited. In the provided code snippet, uint8 is used, which has a maximum value of 255 and a minimum of 0. The add function attempts to add a value to the existing value, and subtract attempts to subtract from it. If you try to add 1 to value when it's at its maximum, 255, it would overflow and wrap around to 0. Conversely, if you try to subtract 1 from value when it's 0, it would underflow, wrapping around to 255. This behavior can result in unpredictable and potentially exploitable conditions in smart contracts. Delegate call pitfalls. In Ethereum smart contracts, delegate call is a low-level function allowing a contract to delegate execution to another contract, potentially leading to unintended behavior or exploits if not used carefully. Essentially, it allows one contract to adopt the code of another contract and execute it as if it were part of the caller's own code, while keeping the original caller's storage untouched. In this example, contract A has a function to set its owner, while contract B uses delegate call to execute A's set owner function. Since delegate call executes A's code in the context of B's storage, the call to set owner actually changes B's owner, not A's. An attacker can exploit this by deploying contract B, then triggering pwen to take ownership of contract B unilaterally. This demonstrates how delegate call can lead to unexpected alterations in contract state if the delegatee's storage layout isn't carefully aligned with the delegator's. Unchecked call return values. In Solidity, when a contract calls another contract, it generates a low-level operation. Low-level calls, such as call, delegate call, and send, return a Boolean value indicating success or failure. Developers must check these return values to handle failures properly. Unchecked call return values can lead to unnoticed errors and vulnerabilities, potentially allowing malicious actors to exploit contracts. This Solidity snippet demonstrates a contract making a low-level call to another contract using the call function, with the method name being the method intended to execute. Importantly, it checks the Boolean result of the call. If the call fails, indicated by a false return value, the contract explicitly reverts the transaction using revert. This pattern ensures that the transaction only proceeds if the call succeeds, thereby mitigating the risk associated with unchecked call return values. Failing to check these values can lead to unexpected behavior or security vulnerabilities. Denial of service, DoS, with block gas limit. A denial of service, DoS attack exploits the block gas limit to make a smart contract functionally unavailable. This is typically achieved by consuming all available gas allotted to a transaction, preventing its execution. One common pattern that results in this vulnerability involves looping over external calls or unbounded operations. In this code snippet, a loop iterates over an array to transfer an amount of ether to each user. If the user's array is large enough, the gas costs can exceed the block gas limit, causing the transaction to fail. This can be exploited by an attacker by increasing the array size, e.g., through actions that add users to the array, thereby preventing the function from successfully executing and essentially denying service to legitimate users. Phishing with tx.origin. The tx.origin vulnerability arises when a contract uses tx.origin to authenticate a user. Instead of msg.sender, which represents the immediate caller, tx.origin refers to the original sender of the transaction. This can be exploited in phishing attacks. The vulnerable contract uses tx.origin for authentication in the transfer ownership function, assuming it's safe to trust the origin of the transaction. However, if a user is tricked into interacting with the attack contract can call transfer ownership on the vulnerable contract. Since tx.origin will still point to the user, the original sender, the ownership can be maliciously transferred to an attacker, despite the user's intention only to interact with the attack contract. This demonstrates the danger of using tx.origin for authentication purposes. Timestamp dependence. In smart contract development, particularly for those deployed on blockchains like Ethereum, timestamp dependence is a well-known security vulnerability. It arises when a contract's logic depends on the block.timestamp, or an alias for block timestamp in Solidity, which is deprecated as of version 0.7.0. Block timestamps can be manipulated by miners within certain limits, making contracts vulnerable to attacks if critical functionalities, like random number generation or mechanism execution, rely on them. This contract attempts to generate a random number once every day by using the current timestamp. However, because miners have some influence over the timestamp of the blocks they mine, they can shift it slightly to benefit their transactions. An attacker could predict or influence the random number by planning a transaction around the time the update random number function becomes callable. This illustrates the risk of relying on block.timestamp for critical contract functionalities, highlighting the importance of considering alternative, more secure methods for random number generation or time-sensitive logic. Randomness attack in smart contracts. In the world of smart contracts, ensuring the unpredictability of random numbers is crucial for the fairness and security of many applications like lotteries or games. However, achieving true randomness on a transparent and deterministic platform like Ethereum is challenging. The randomness attack exploits the predictability of the method used to generate random numbers in a smart contract, allowing attackers to anticipate outcomes potentially. This code snippet illustrates a simplistic smart contract for a guessing game, intending to generate a random number for each guess. It leverages Keccak 256 hashing of the current timestamp, now, and an initial seed derived from the deployment timestamp and deployer's address. However, because now, alias for block.timestamp, is publicly visible and the seed remains unchanged, an observant attacker can predict the random number by executing the same hash function off-chain. This predictability undermines the randomness, making the contract vulnerable to a randomness attack. Front-running and transaction ordering dependence. Front-running is a scenario in the blockchain world where a malicious user observes another user's transaction in the pending transaction pool, mempool, and attempts to get their own transaction mined first by paying a higher gas price. Transaction ordering dependence refers to smart contracts whose outcomes depend on the order of transactions, making them vulnerable to manipulation by miners or others who can influence this order. In the given code snippet, a function updatePrice updates the price of an asset. If this transaction is seen in the mempool, a frontrunner might execute another transaction that benefits from knowing the new price before it's publicly updated by offering a higher gas fee to get their transaction mined first. This vulnerability can lead to unfair advantages and financial losses for unaware users. To mitigate such risks, smart contracts can use mechanisms like commit reveal schemes, or depending on the context, time locks and batch processing to disaggregate the timing from transaction submission or order. Using linters and security-focused Solidity plugins. Linters are tools that analyze source code to flag programming errors, bugs, stylistic errors, and suspicious constructs. In the context of Solidity, security-focused linters and plugins help developers avoid common mistakes and ensure best practices in smart contract development. An example of such a tool is Solhint, which can be configured to emphasize security rules. This JSON configuration snippet for Solhint demonstrates how to extend the recommended rule set with a specific focus on security by including the security plugin. Additionally, it customizes the rules to warn about the use of inline assembly, a feature that can lead to security vulnerabilities if misused, and to throw an error for low-level calls, which are often risky as they bypass the type safety of Solidity. By configuring linters in this way, developers are actively prompted to write safer, more secure smart contracts. Automated analysis tools, Slither, Securify, MythX. In the realm of smart contract security, automated analysis tools play a pivotal role in identifying vulnerabilities. They automate the detection of common security issues, saving time and enhancing the security audit process. We'll explore 3 prominent tools, Slither, Securify, and MythX, each with its unique approach to static and dynamic analysis. The provided smart contract contains a re-entrancy vulnerability in the withdraw function. It attempts to send Ether before zeroing out the sender's balance, allowing for potential re-entrancy attacks. Automated analysis tools such as Slither can statically analyze this code and warn about this re-entrancy risk. Securify would assess the contract patterns against its database of known secure and vulnerable patterns, likely flagging the unsafe call method. MythX, implementing both static and dynamic analysis, could detect the anomaly through execution trace inspection. Each tool aids in uncovering vulnerabilities from different angles, emphasizing their value in smart contract development and audit processes. Formal verification of smart contracts. Formal verification is a process that mathematically proves or disproves the correctness of a smart contract's algorithms relative to a certain formal specification or property. It involves creating a mathematical model of the smart contract to ensure it behaves as expected under all possible conditions. This can drastically reduce the risk of bugs and vulnerabilities. In this code, a simple Solidity contract uses SafeMath to prevent overflow errors, a common issue in smart contracts. Formal verification would involve creating a mathematical model of the add function to verify it accurately executes addition without causing overflow under any condition. If the model proves this property, the function can be deemed secure against overflow vulnerabilities. This process involves specifying the expected behavior, e.g., for any inputs A and B, the sum C will not overflow, and using verification tools to analyze the code against the specified behavior. Smart contract audit techniques. Smart contract audits are crucial for identifying vulnerabilities and ensuring contract integrity before deployment. They involve both automated tools and manual inspection to review the contract code thoroughly. This Solidity code snippet represents a basic smart contract that provides a simple storage service. To audit this contract, auditors would typically employ automated scanning tools first to identify common vulnerabilities, such as re-entrancy, overflow, underflow, or gas limit issues. Following the automated scan, a manual review would scrutinize the contract's logic, access controls, and state management to ensure compliance with best practices and detect potential security flaws not caught by automated tools. Techniques include checking for proper validation of inputs, ensuring no sensitive functions are publicly accessible without proper authentication, and verifying that state changes are correctly managed to prevent unintended consequences. Security patterns and best practices. In smart contract development, following security patterns and best practices is crucial to mitigate vulnerabilities. We'll explore a fundamental pattern, the checks effects interactions pattern, which aims to prevent re-entrancy attacks. This code demonstrates the checks effects interactions pattern to prevent re-entrancy attacks. Initially, it checks if the withdrawal amount is available, checks. Next, it updates the sender's balance before transferring any ether effects. Finally, it performs the ether transfer interactions. By ensuring the effect, balance deduction, happens before the interaction, ether transfer, it mitigates the risk of re-entrancy attacks where an attacker could repeatedly call withdraw before their balance is updated. Bug bounties and security contests. Bug bounties and security contests are popular methods used by organizations to identify and fix vulnerabilities in their smart contracts. They incentivize security researchers and hackers to ethically disclose bugs by offering rewards. This process helps improve the security of smart contracts before they are exploited maliciously. The above code represents a simple, vulnerable smart contract that could be a target for bug bounties. It contains a re-entrancy vulnerability in the withdraw function, allowing an attacker to repeatedly withdraw funds. Bug bounties would encourage individuals to report such issues for a reward, contributing to the contract's security before it faces real-world exploitation. Security contests could also involve analyzing contracts like this for vulnerabilities, promoting learning and improvement among the security community. Cross-chain interactions and security implications. Cross-chain interactions enable blockchains to communicate, sharing data and value. This is vital for decentralized finance, DeFi, and other applications. While powerful, they introduce unique security concerns, particularly regarding the integrity and trustworthiness of the data being exchanged. The code represents a simplistic cross-chain transfer function within a smart contract. It highlights the concept of sending assets from one blockchain to another, which involves coordinating between different blockchain protocols. The security concern here is double spending across chains and ensuring the accuracy and legitimacy of the transaction data received from another chain. Validators or oracle networks often mediate these transactions, which introduces a point of vulnerability. Ensuring the robustness of cross-chain protocols and the oracles that support them is critical to preventing exploits such as replay attacks or data manipulation. State channels and off-chain computations. State channels are a second-layer solution for enabling off-chain transactions while retaining the security guarantees of the blockchain. They allow participants to conduct numerous transactions off-chain, with only two on-chain transactions, one for opening the channel and one for closing it. This greatly reduces gas costs and increases transaction throughput. Off-chain computations are done by participants outside the blockchain, and then the final state is agreed upon and submitted to the blockchain. This can involve complex calculations or simply counter increments. While specific code for implementing state channels or off-chain computations varies widely depending on the application and blockchain, the core concept involves participants locking in some state on-chain, e.g., depositing funds into a smart contract, then performing transactions off-chain by signing messages or transactions with their private keys. These off-chain transactions can represent anything from payment channels, gaming moves, to votes in a decentralized application. Finally, the participants submit the final state back to the smart contract on-chain, which then updates the on-chain state to reflect the off-chain activities. This drastically reduces the on-chain load and gas fees, making applications more scalable. Oracle design and the oracle problem. In the context of blockchain and smart contracts, an oracle is an agent that finds and verifies real-world occurrences and submits this information to the blockchain to be used by smart contracts. Smart contracts cannot access real-world data directly due to their deterministic nature. Thus, oracles serve as bridges between the on-chain and off-chain worlds. However, this introduces the oracle problem, which revolves around the trust and security issues stemming from relying on external information sources. The code example depicts a smart contract interfacing with an oracle. Through the IO Oracle interface, it defines two functions: request data, which allows the contract to request data from an external source, specified by a URL and a path within the retrieved data, and get data, which allows the contract to fetch the requested data if available. The myContract constructor takes an Oracle address, setting up a direct link to the Oracle. Request external data function illustrates how a smart contract might ask an Oracle for external data. This setup is foundational for dealing with the Oracle problem by establishing a structured way to interact with oracles whilst highlighting the dependency on external, potentially centralized data providers. Upgradable smart contracts and proxy patterns. Smart contracts, once deployed, are immutable. However, developers often need to update their code to fix bugs or add features. Upgradable smart contracts using proxy patterns allow for such modifications without losing the contract's state or address. The most common pattern is the transparent proxy pattern, which separates the contract into two main parts: the implementation, logic, and the proxy, state and delegation. In this example, proxy is a generic proxy contract that delegates all calls to an implementation v1 contract, which contains the logic. The set implementation function in the proxy contract allows for the updating of the logic contract. Use of delegate call allows the logic contract to execute in the context of the proxy contract, meaning it uses the proxy's state while executing the logic's code. This is how upgradability is achieved without losing state. The proxy pattern separates concerns, enabling developers to upgrade the contract's logic without altering the stored data or contract address. Gas optimization strategies. In smart contract development, minimizing gas consumption not only enhances performance, but also reduces transaction costs for users. Several strategies can be employed to optimize gas usage, such as using efficient data types, minimizing storage operations, and simplifying function logic. This example demonstrates a simple gas optimization technique through efficient code logic. The function isEven checks if a number is even. This is achieved without using loops or additional variables, which minimizes gas consumption. Utilizing the modulo operator sent directly to compare against 0 is a straightforward approach that conserves gas. In smart contracts, it's crucial to aim for simplicity and avoid unnecessary complexity in functions where possible to save on gas costs. Layer 2 scaling solutions and their security considerations. Layer 2, L2, scaling solutions are designed to increase the throughput of blockchain networks without compromising on decentralization or security. These solutions operate on top of the base layer, Layer 1, providing faster and cheaper transactions. Among the most popular L2 solutions are state channels, sidechains, and rollups. Understanding the security considerations of these solutions is crucial for developers to protect against potential attacks and vulnerabilities. The sample code illustrates a simplified Solidity interface for a Layer 2 scaling solution. This interface includes functions for depositing and withdrawing funds, which are fundamental for interacting with L2 solutions. When implementing or interacting with such contracts, it's crucial to consider their security aspects. For instance, ensuring the contract correctly handles deposit and withdrawal requests to prevent double spending or funds being locked up incorrectly. Additionally, the integrity and security of the bridge between Layer 1 and Layer 2 are pivotal, as vulnerabilities here could lead to significant losses. Introduction to DeFi and its unique security challenges. Decentralized finance, DeFi, represents a shift from traditional, centralized financial systems to peer-to-peer finance enabled by decentralized technologies built on the Ethereum blockchain. DeFi leverages smart contracts to create protocols that replicate existing financial services in a more open, interoperable, and transparent way. While this code snippet does not directly reflect the complexity of DeFi protocols, it serves as a basic framework illustrating how smart contracts are the building blocks of DeFi applications. DeFi's unique security challenges arise from the immutable and transparent nature of blockchain technology, coupled with the composability of DeFi protocols, where one's protocol can directly interact with another. This increases the risk of exploits due to vulnerabilities, such as reentrancy attacks, flash loan attacks, and issues with price oracle manipulations. Ensuring the security of DeFi protocols involves diligent smart contract auditing, rigorous testing, and employing best practices in smart contract development. Common DeFi attack vectors. Decentralized finance, DeFi, has revolutionized the financial sector by leveraging blockchain technology to facilitate financial transactions without intermediaries. However, DeFi platforms and smart contracts are susceptible to various attack vectors. Understanding these can help in devising safeguards against potential threats. We'll cover some common DeFi attack vectors, showcasing typical vulnerabilities. DeFi platforms often face issues like re-entrancy attacks, where a malicious contract calls back into the function it's executing to drain funds. Flash loan attacks utilize uncollateralized loans to manipulate market prices for personal gain. Oracle manipulation involves tampering with the data source that a smart contract relies on for external information, leading to adverse outcomes. Lastly, inadequate access control can allow unauthorized users to exploit certain functions that should have been restricted. These attack vectors highlight the need for meticulous smart contract security practices, including thorough testing and employing external audits. Flash loan attacks and defenses. Flash loan attacks exploit rapid loan mechanisms in DeFi protocols, allowing attackers to borrow huge sums without collateral. These funds can manipulate market prices or exploit vulnerabilities, resulting in significant financial losses. Defenses involve careful coding practices and financial safeguards. The code snippet illustrates a basic defense against flash loan misuse by implementing a fee for flash loan operations, aiming to deter attackers by increasing the cost of attack. The flash loan function requires a specific fee to be paid, flash loan fee, by users wishing to initiate a flash loan. By mandating this fee, the contract attempts to add an economic burden on potential attackers, discouraging frivolous or malicious use of flash loans. Composability risks in DeFi. Composability in DeFi refers to the ability of different protocols and platforms to work together seamlessly. While this leads to innovative financial products, it also introduces complex interdependencies that can amplify risks, such as vulnerabilities spreading from one protocol to another. The provided code illustrates a basic idea of composability, where a function within a DeFi contract interacts with various protocols through a loop. While this demonstrates the power of composability, it also surfaces risks. If any of the referenced protocols contain vulnerabilities or become compromised, the effects can quickly spread to this contract and potentially to others that interact with it. This interconnectedness can lead to systemic failures within the DeFi ecosystem, underscoring the importance of thorough security diligence for each component in a composable stack. DeFi-specific security tools and techniques. When developing smart contracts for DeFi applications, employing specific security tools and techniques is vital to mitigate risks. One common technique is to use decentralized oracles for external data to ensure its accuracy and reliability. Let's look at how Chainlink, a popular decentralized oracle network, can be integrated into a smart contract. This code sample implements a smart contract that uses Chainlink's oracle network to fetch the latest price data for a specific asset. The contract imports Chainlink's aggregator v3 interface, allowing it to interact with an oracle. A price feed address is passed to the constructor to specify which oracle to use. The getLatestPrice function then calls latest round data on this oracle, returning the latest price it provides. This technique ensures that the smart contract receives accurate, up-to-date external data, mitigating risks associated with using unreliable or manipulated data sources. Case studies of DeFi hacks and lessons learned. This lesson examines several notable DeFi hacks, focusing on the vulnerabilities exploited and the lessons learned. Understanding these incidents is crucial for developing more secure smart contracts. One significant DeFi hack involved the exploitation of re-entrancy vulnerabilities. Hackers executed recursive calls to a contract, withdrawing funds repeatedly before the initial transaction was marked as completed. This led to substantial losses. The lesson learned emphasizes the importance of using re-entrancy guards, such as the OpenZeppelin's re-entrancy guard contract modifier, to prevent such attacks. This incident highlights the need for meticulous security practices, including thorough testing and leveraging established security libraries where possible. The importance of audits in the smart contract development process. Smart contracts are self-executing contracts with the terms of the agreement directly written into code. Since they automate transactions and enforce agreements without intermediaries, they must operate flawlessly to prevent loss of funds or unintended consequences. Audits are critical in verifying the security and correctness of these contracts. The provided code snippet is an example of a very basic smart contract written in Solidity, the primary language for Ethereum smart contracts. It allows for storing and retrieving a number. While seemingly straightforward, even such simple contracts need auditing. An audit examines the contract's code for security vulnerabilities, logical errors, or deviations from best practices. For instance, without proper access control, any user could alter the stored data, leading to potential misuse. Here, although our contract is simple, in practice, contracts are much more complex, containing critical operations like managing funds, where mistakes could lead to significant financial losses. This underscores the importance of thorough audits in the smart contract development process to ensure security, functionality, and reliability. Phases of a smart contract audit. Smart contract security audits are critical for ensuring the reliability and security of blockchain applications. These audits are typically conducted in several phases to meticulously examine the smart contract code for potential vulnerabilities. The phases of a smart contract audit start with specification gathering, where auditors understand the intended functionality. Next, static analysis is performed using tools to examine code without executing it, whereas dynamic analysis involves code execution to expose vulnerabilities. The manual review phase involves human experts analyzing code to catch issues automated tools might miss. Report preparation encompasses documenting findings, risks, and recommendations. Finally, remediation and re-audit involve fixing identified issues and verifying corrections, ensuring the smart contract's security and reliability. Audit techniques and methodologies. An effective smart contract audit aims to identify vulnerabilities, errors, and deviations from best practices in smart contract code. To achieve this, various audit techniques and methodologies are utilized, combining automated tools and human expertise. This pseudocode represents the use of an automated tool in smart contract audits. Automated tools can quickly scan code for known vulnerabilities, helping auditors to pinpoint potential issues efficiently. Despite their utility, they're not foolproof and must be complemented by manual review to catch complex vulnerabilities that automated tools might miss. The blend of both approaches ensures a thorough examination of the smart contract code. Common findings and remedies in smart contract audits. Re-entrancy attacks occur when an external contract calls back into the current contract before the first execution is finished, potentially draining funds. A common remedy is to use the checks effects interactions pattern to avoid unforeseen re-entrancy. The code above demonstrates a secure withdrawal function avoiding re-entrancy attacks. It first sets the user's balance to 0, then attempts to transfer funds, effect, and checks for transfer success interaction afterward, following the checks effects interactions pattern. Working with external audit firms. When engaging with external audit firms for smart contract security analysis, it's crucial to streamline the process to ensure both sides achieve the most value. This usually involves preparing your codebase, setting clear communication lines, and understanding the audit process. The provided code snippet is an example of a function within a smart contract that might be submitted for an audit. Before submission, developers should ensure the code is clearly commented, well-structured, and that it includes comprehensive testing scripts. This facilitates the auditor's understanding of the intended functionality and logic flow, allowing for a more effective and efficient audit process. Understanding how auditors review each line and functionality for potential security risks enables developers to prepare their code for scrutiny, aligning with best practices for smart contract security. Post-audit considerations and security guarantees. After a smart contract audit is concluded, there are critical steps and considerations that must be understood to enhance and maintain the security posture of the smart contract. This phase involves analyzing the audit report, addressing discovered vulnerabilities, and understanding the limits of security guarantees. The code illustrates how to address a typical vulnerability related to unchecked external inputs that could potentially lead to exploits such as reentrancy attacks or overflow-underflow issues. By including checks like require amount 0, the contract ensures that only valid operations are processed. Post-audit, it's essential to review all vulnerabilities listed in the audit report and apply necessary fixes like these. However, security guarantees are limited to the scope of the audit, and ongoing vigilance is required to address new vulnerabilities that may arise post-audit. Regulatory landscape for smart contracts. Understanding the regulatory landscape for smart contracts is crucial for developers and users to ensure legal compliance and minimize risks. This landscape varies by jurisdiction, but typically involves considerations of contract law, financial regulations, and technology-specific legal frameworks. There's no one-size-fits-all regulation for smart contracts, as legal frameworks vary significantly around the world. In many jurisdictions, smart contracts are subject to traditional contract laws, provided they meet the criteria for contract formation. Issues like enforceability, jurisdiction, and consumer protection are key concerns. Additionally, certain smart contracts, especially those handling financial assets, may fall under specific financial regulations such as the Securities and Exchange Commission (SEC) in the USA or the Financial Conduct Authority (FCA) in the UK. Developers must be aware of and comply with these regulations to ensure the legality and longevity of their smart contracts. Ethical considerations in smart contract development. Ethical considerations in smart contract development encompass the responsibilities and moral obligations developers have towards users. This includes ensuring accuracy, fairness, and transparency in the contract's operations, protecting user privacy, and considering the potential social impact. Ethical development practices are essential to gain user trust and foster a sustainable ecosystem. In the provided code example, the terms variable is declared as public to ensure transparency, allowing users to understand the contract they are interacting with. This is a crucial ethical practice, as it respects the user's right to be informed. Additionally, including a resolve dispute function demonstrates an ethical consideration for fair treatment, providing a mechanism to address grievances. This reflects a commitment to fairness and user protection, crucial aspects of ethical smart contract development. Smart contracts and digital identity. Digital identity in smart contracts refers to representing an individual's identity traits using digital means within a blockchain. This enables secure and tamper-proof identity verification and management. It's vital in ensuring only authorized parties enter agreements, enhancing security and trust in digital transactions. The code snippet defines a basic smart contract for digital identity management. It allows storing and verifying identities mapped to Ethereum addresses. Add identity associates an identity with a user's address, and verify identity compares the stored identity's hash with a given hash, enabling secure identity verification without revealing the actual identity data. This approach leverages the blockchain's tamper-proof nature, ensuring that identity data remains secure and unaltered. Data privacy regulations and considerations. Understanding data privacy is essential when developing smart contracts, especially those handling personal data. This involves adhering to regulations like GDPR in the EU, which mandates the protection and lawful handling of personal data. An essential step is anonymizing or pseudonymizing data before storing it on the blockchain. Below is a simple smart contract example demonstrating the concept of data minimization and pseudonymization. The provided smart contract showcases a basic approach to handling user data in a privacy-compliant way. Instead of storing personal data directly on the blockchain, it stores a hash of the data. This method pseudonymizes the data, making it difficult to trace back to its owner without additional information that's kept off-chain. The mapping user data associates user addresses with hashed data, ensuring data is both obscured and retrievable only by specific addresses. This approach helps in adhering to data minimization principles, a core aspect of many data privacy regulations like GDPR, which states that only necessary data for the specified purpose should be processed. Consumer protection in the context of smart contracts. Consumer protection within the realm of smart contracts highlights the necessity to safeguard users from fraud, enforce transparency, and ensure the right to privacy. It emphasizes the implementation of mechanisms that protect consumers' interests while interacting with these digital contracts. The provided smart contract example illustrates a basic consumer protection mechanism within a sales context. By declaring an event purchase, it ensures that transactions are transparent and traceable. The only seller modifier restricts function execution to the seller's address, preventing unauthorized actions. Emitting an event upon a successful purchase explicitly records the transaction on the blockchain, providing an immutable record for dispute resolution or auditing, thereby protecting consumer interests.